I was up here jamming to the music. I forgot to read the intro. RockTrue Science is a cross-cultural response to the lack of diversity in STEM fields. STEM stands for science, technology, engineering, and mathematics. RockTrue Science is designed to serve the intellectual need of fallen man, while serving the desire for interdependence to better understand our physical world while still pursuing spiritual growth. RockTrue Science seeks to inspire, enlighten, and highlight upcoming and established local and international kings and queens of STEM fields while promoting Black consciousness and awareness of who we are and to whom we belong. Happy Tuesday, everybody. I don't know. I don't know why that's showing up. It's making like me look pink or something. I don't have a filter on. It's just my camera being my camera. Say hi, bud. What is she looking like that? Hey. Wave. So today we are all up in the organic chemistry section of the chart because organic chemistry is based on carbon. So anything that has carbon in it makes it an organic substance. So that's why they call us carbon-based beings, because we are carbon-based. Like pretty much every cell in our body has some type of carbon compound, molecule, structure, or something in it, and we'll definitely be getting into that a little bit more deeper. I made sure I found some nice little pics of the different, types of carbon, commonly found carbon compounds in our bodies, because, it's just nice to put that into perspective. But this is group 4, or technically, depending on which naming process you're using, is group 14. It's on the other side of the transition metals, right next to the boron group that we did last week. So these are called the crystallogens, or the carbon group. So everything in this group is it follows a nice trend. So normally when you go down a group, there's a trend of things that occur. So with this, as you go down the group, so as the elements get larger in size, in atomic size, they increase in ionization energy, meaning it takes more in it. That's right. Increasing. Yes. The atomic radius increases and the ionization energy decreases because those outer or valence electrons are further. You adjusting my mic. That's my production team. She helping. Thank you. So as the electrons get further from the positively charged nucleus, it's easier to pluck those electrons out of those outer shells than in a very small, tightly spaced element like carbon. Carbon has its proton positively charged nucleus, and it's got 4 electrons hanging around. So we did kind of touch on electron orbitals in some of the earlier shows, but of course we're going to say it as many times as y'all need to hear it to remember it. Okay. Mm-hmm. So the innermost shell is the 1s orbital, and it can only hold 2 electrons. And then there's the 2s orbital just outside of that holds 2 electrons. And then the very outer shell of carbon, you get your p orbital, and it has 2 electrons in it. So you have a total of your 6 electrons. But due to, and this is one of those groups that ends up getting that, due to the inert pair effect, only 2 of those electrons tend to bond or leave when they're ionized. They tend to be the ones that ionize. So group 4, you would expect the group 4 elements to have a +4 ionization state, but they don't, due to the inert pair effect. So the ones on the very outer shell in the 2p orbital, well, for carbon it's 2p, but it follows a trend of, depending on whatever number of shells, but the outermost shell of all of these elements: carbon, silicon, germanium, tin. We did that experiment 10 with the tin hedgehog. Remember that one? Lead and fluorovium. All of their outermost shell of electrons is a p orbital. and they all have 2 electrons in it. So due to that effect, those electrons are lost easiest. Hey, thanks for coming. We can't see you because you're not logged in, so I'm not sure you. Okay, Alexis. Hey, thanks for coming, sis. That's my sorrow, yeah. But the outermost shell loses its electrons, and so you end up with a +2 ionization state, and the larger elements can actually reach a +4 ionization state. Carbon ain't doing that. Carbon not going to do that. It's going to form a bond before it decides to lose electrons and have a positive ionization state, which is why you normally see why carbon is like kind of like the anchoring element in all of the organic compounds, because it is extremely stable, for one, because it can form 4 bonds with 4 other stable elements, and the compounds that carbon tends to form is also stable within itself. And that being said, there are what is that one? The fullerenes, I believe it's the fullerenes, but there it's carbon has allotropes, and the allotropes are basically just different forms of carbon. So people love diamonds, and diamond is an allotrope of carbon. So it is all carbon. Diamond is all carbon, and it's just a different form. It's a crystalline, very organized and hard structure of carbon, and the purity of the diamond is usually what's increases its value. So diamonds are formed, and then there are other minerals and things that can get trapped inside of it, and that's what makes the color different, and the the luster and all. I don't know how to value diamonds, but all the stuff that makes diamonds nice and sparkly and pretty depends on how. Hey, Ty. Depends on how pure the diamond was made. So like if it was like a lot of minerals and stuff mixed into the carbon and the coal and stuff that was forced and pressured into diamond, and I believe it's only naturally occurring. So that's where you get the fake diamonds that are made. They tend to use other minerals, and I know, right? Dust off them chemistry books. Because I was reading it. I was like, this is way too sciencey for this show, but I'm going to write it down anyway because I like this is interesting. But yeah, diamond is all carbon, and then you have buckyball, so like buckshot way back in the day. I'm not sure if they still use it's called like Buckminster fullerene. It's a scientist who discovered it. It's named after him. That's why it's called Buckminster. Trust me, they wouldn't name it that on purpose if it wasn't a person's name. But fullerene is another allotrope of carbon, and fullerenes are tend to be used in industrial processes, and also anchoring other metallic processes that need anchoring. So like it stabilizes other unstable metallic reactions and processes and things like that. Then graphite. So everyone knows about the graphite in their lead pencil is not actually lead. I remember when I was a kid, they was like, if you get stabbed with a lead pencil, you can get lead poisoning because it's lead. That's not it. That's not it. So it's called lead, but it's not actually the elemental lead. But it is a mixture of carbon in its graphite form, which is kind of like it has a slippery characteristic to it, which is why your pencil glides across the paper as it does, and it's mixed with some clay and stuff to kind of beef it up and give it some color. But for the most part, it's made of graphite. And I think that's all the most important allotropes, but it has a bunch of other very stable forms, and like I said, whatever it's mixed with forms stable compounds. And all of the other elements in this group tend to do the same thing, except fluorovium is very radioactive, and it's very rare, and it's very short-lived, so you probably won't hear much about it, and not whole lot of research has been done because it's not important. Like we don't really use radioactive stuff as much because it's toxic to everything. So unless it has, was accidentally found or purposely found to have a big use, and it's not that rare, because the rarer things are, the more expensive it is, the harder it is to find. And then if you have to use a lot of it to test through things and figure out what works, you might end up using it all up trying to figure out what works. So, they was like, it's not worth it. And silicon, the next one in line, is basically sand. So it is the second most abundant mineral in the Earth's crust. Talking about, I see you living your best life. Living my best life. Hey, Marley King. So as we can see, silicon is the second most abundant mineral in the Earth's crust because the Earth has a ton of sand. So you think of the beach sand, but under all of that water, all around the globe, there's sand under there too. So that's why silicon is super abundant, and that's actually what we use to make glass. So basically, there's a combustion process with silicon, and we'll talk about combustion too. That's a nifty little process. I got some videos for that, because you gotta see it in motion. It doesn't do it just throwing up a picture and talking about that. You definitely got to see that one in motion. But silicon gets combusted with air and it forms glass, and you get silicon dioxide. So that's actually what black sand, I believe it has something to do with the like the impurity. Well, it's not impurity, but it's not just silicon. Like there's also white sand. So those are allotropes of silicon. So like and we actually talked about tin. So tin has different color allotropes. One is called alpha tin and the other one is beta tin. So alpha tin, he said, are you eating ice?
Because the whole time, oh my God, like I forgot. Listen, I didn't forget that I actually been over here with my volume on, so you can hear the whole time. I've been tearing this ice up. Nobody told me. Why you ain't say nothing?
You're right. It's okay.
Okay, all right. Let me go back to Ty. Thank you, Ty. Yes, with me.
She destroyed that. Yes. You know she got the big coat. You know she all ice. I got my green Kool-Aid. Right, green. I don't know the flavor. It's green. You muted now. Now I can't hear you.
Oh, I'm like, you always get something new. You never tell nobody. See, this is not the day for me. This is not the day for me. I'm on Wednesdays throwing up the W, okay?
Right. Talk about it Tuesday.
I promise I was getting that thing. Since I'm embarrassed. I cannot. Let me go back. My bad.
No worries. So tin has two different allotropes, and they are going ham on the ice like it's the Last Supper. Yeah. Woo, it's warm now. So tin has two allotropes that show up at different temperatures, and at lower temperatures, like cool temperatures, you get beta tin, which beta tin is that beta alpha tin, which is the gray tin. Did I write that down right? We'll see. I probably have them switched up, but you get one form of tin which is called gray tin, and it's a powdery kind of situation. But silica and silicone, silica is usually referred to for just the element. Well, not the element, but it's usually like a double molecule or a molecule of silicon, not like bonded with anything else. So it would probably be like a triple bond to itself or something like that, or a double bond, some type of situation with hydrogen in there, because hydrogen loves to bond to this group. So you'll see a lot of methane around. So CH4 and all of the things, all of the other elements in this group make similar bonds like carbon does, but carbon binds more strongly to stuff because of its smaller its smaller atomic size. And the other ones in this group are actually metalloids. So they don't behave quite the same way that carbon does. Carbon is the only non-metal in this group, kind of like boron. And its group was the only non-metal, and everything else in that group was actually metalloids or radioactive material. And in this group, silicon is a metalloid as well, and germanium, and then tin and lead, as we know, are actual metals and semiconductors. And then fluorovium, like I said, is a radioactive compound. So that's where those are. A lot of times, like, we have a lot of common names for these things, like cyanide is actually an acid. So it's usually found in an acid form because it interacts as an anion. So CN is carbon and nitrogen. So it's actually a molecule. Cyanide is a molecule. It's not just one thing. And then you get hydrocyanic acid when you add the hydrogen to it, and that's its actual chemical name. And then we tend to come up with common names for things because the scientific name, the actual chemical name, can be longer, more complicated, and all of that. So that's kind of how the names and stuff get kind of spoofed around. And then also depending on what acidic form or how much oxygen is bound to. So like the acids. So if you do like sulfuric acid, or even with carbon, because carbon forms different bonds. So you can get CO2 and CO, so carbon dioxide, carbon monoxide, those are its actual chemical names. And then depending on where it's used and how it's used, it probably has a different common name. Like when they say carbonation in drinks and pop and stuff, the bubbles, that's literal carbon dioxide bubbles. And it's just trapped, like super packed into the drink. So that's where all of that comes in, and that's why it goes flat, because eventually all the carbon dioxide bubbles, move out of the drink and back into the atmosphere, because it's lighter than usually whatever it's in, because it's a gas, and what is in is usually like a syrup. So that's kind of how the name, like the naming and stuff with a lot of the compounds kind of go. They have the IUPAC. I forget what that stands for, but that's essentially what it is. When they say the standard chemical name is usually following an IUPAC standard, and then if it's not an IUPAC name, it's just a common something, or like renamed for its common use, because sometimes things are just named after what they're used for instead of what they actually are. And tin, actually, is that tin or lead? Tin, obviously not lead, because lead is toxic to us. Oops. So tin is actually used in fluoride in your toothpaste. So the toothpaste that's fortified with fluoride is actually a tin fluoride compound. Yeah. And it's the anti-cavity thing. So it helps deliver the fluoride to your teeth. And I didn't look into the chemistry of that, so I'm not sure why they use tin for that, but I'm pretty sure it has something to do with the fact that it has a much lower ionization energy than carbon does. So if you use carbon, it would never let go of the fluoride for us to be able to use it in our teeth. So it had to be a larger element that was happier with releasing the fluoride to our teeth, that has probably a much lower ionization energy, and grabs the fluoride out of it. Yeah, I was like, oh, that's what they using. So yes, I know, right? When you do research, you find all kinds of stuff. It's like, oh, so carbon is like super important for life on Earth. Like oxygen, carbon is like right in there. So how should I put this? The carbon cycle is like up there with the water cycle, photosynthesis, your metabolism and stuff like that. So the carbon cycle is basically like the metabolism of carbon in the world. So like between the atmosphere, our planet, and the water. So, oh yeah, you got that video. You can pull that video up, and it should be the one carbon cycle, and it's like a quick, probably like 2.5, 3 minute video,
Okay.
and it goes through all of where carbon, it doesn't, like, there's no start because it's a cycle, so it's like never ending. It's a circle of life. Oh, we can't hear.
Can you hear me?
Now we can.
Okay, hold on. Let's try it again. It's crazy. Hold on.
Still can't hear it.
Go ahead. Give me just a second. Let me check my settings on my end. But go ahead, keep talking.
Okie dokie. And so this is kind of like another reason why it's like good to understand, like, not just the elements, but how they fit into our lives, because this is why deforestation is a problem, the greenhouse effect, global warming, all of that stuff. This is why it's a problem, because it kills plants, and it makes it hard for them to grow and flourish and get all green and leafy and all of that, because we need plants to bring carbon to the earth and make it able for us to ingest it and metabolize it and use it in our bodies. And it's important. Yes, there we go. Yeah, we can hear it.
Component of our atmosphere. Carbon. Welcome to Moo Math and Science and the carbon cycle. Carbon is an element that is vital to most living organisms on Earth. It is also a key component of our atmosphere. Carbon has the ability to cycle through our Earth, the ocean, living factors, abiotic factors in the air. The carbon recycles among 5 major locations. These items include the atmosphere, the terrestrial biosphere or land, the Earth's interior, the ocean, and human influence. Let's take a look at what happens at each of these areas. Carbon is found in the atmosphere in at least 2 forms, carbon dioxide and methane. This atmospheric carbon can be absorbed by autotrophs like plants and plankton to be used for photosynthesis. It can also be absorbed by bodies of water and the ocean. When carbon is absorbed by the ocean, it reacts with the water and creates carbonic acid. The terrestrial biosphere, which is another term for the Earth's land, has several paths of carbon that it can take. First, there is an exchange between plants and animals. Plants absorb carbon in the form of carbon dioxide for photosynthesis, and animals release carbon dioxide during cellular respiration. Also, heterotrophs eat plants that contain carbon. Animals also release carbon as methane during digestion, and the soil contains decomposers that release carbon into the atmosphere and the soil. Carbon is also stored in the Earth's interior. Carbon in the lithosphere includes fossil fuels like coal, oil, and natural gas, along with deposits like limestone. And volcanoes may release some of this carbon stored in the lithosphere when they erupt. Up next, the ocean. The ocean has the greatest exchange quantity of cycled carbon and stores a large amount of carbon. The ocean absorbs carbon in the form of carbon dioxide. The ocean also has a large amount of plankton that absorbs carbon dioxide that it uses for photosynthesis. Humans also influence the movement of carbon. Humans burn fossil fuel, which releases carbon dioxide into the atmosphere. Also, the production of clinker, which is used for cement from limestone, also releases carbon. In addition, deforestation from humans can cause the amount of carbon in the atmosphere to increase. So there you go, an overview of the path of an atom of carbon that may take place during the carbon cycle. Thanks for watching, and Moo Math uploads a new math and science video every day. Please subscribe and share.
So that's why I said that's one of those things you got to see it. You can't. It's hard to describe, but it makes more sense when you see it. So as you can see, we heavily influence the direction, the flow, and the movement of carbon in our environment, through the environment. And as we said, deforestation causes a lot more carbon to stay in the atmosphere, meaning that it increases those greenhouse gases, because greenhouse gases are like methane, which is why not livestock, so the poop that they show, but gas, like also like literally like the gas, like if they pooped, all of that is methane, and it leaches into the groundwater, so like that's a problem. But it also I'm not sure if people know what the greenhouse effect is. I probably should have pulled a video up of that, but we'll end up talking about that later as well. But what it does is it basically just makes it hotter in here because it can't get out because of the ozone. So the ozone layer actually traps it in and makes it's like if you put like a mirror up and the sun reflects off the mirror, it's like way hotter and stuff. You can, or like use a magnifying glass, kind of like that. She's back. So that's why it's a problem. And what's going on? What's the problem? And that's why I love the idea of like rooftop gardens. So like if you have like a flat roof, especially like in cities, so either solar panels or a rooftop garden. Like, come on now, we got to use the space to get some sustainable stuff going. And so rooftop gardens help with smog. So I think that was actually an initiative in a couple of different heavily industrial cities was doing that, because it does help with smog because the plants clean the air. And then so carbon is special in that it can form molecules that have negative charges and act as a halide. Duda, you got your whole forehead in the camera. And so carbon being so versatile is also why it's the basis to pretty much everything. So in the carbon cycle, so what we saw, okay, Duda. So what we saw the plants doing, I know, right? What's the problem? I thought you wanted to get down. So what the plants do is they carbon fix. So they also nitrogen fix, and we'll be talking about that next week because nitrogen is the next group. And so when they carbon fix is basically they pull it out of the atmosphere and they make it into an organic form that we can use, other animals and other things can use that don't have photosynthetic capabilities. So as you saw, the plankton in the water also do photosynthesis, and that's why it's a ton of carbon fixed in the oceans, because the plankton in there use it and draw it into the water. Go ahead, Duda. I don't know what she was trying to do. And then, so in order to use this fixed carbon, you have to do combustion. And combustion basically releases the carbon from whatever the fixed forms are. So plants end up fixing carbon into carbohydrates or starches in their chlorophyll cells and stuff like that. So when we eat plants and we eat things that eat plants, we can get that carbon back out of it by combusting the sugar molecules. And I also have a video for that. Yeah, we can go ahead and do the combustion video too.
Humans do a lot of burning. In the past, we burned a lot of wood, and we still burn some. We burn huge amounts of the fossil fuels, coal, oil, and natural gas. Sometimes we burn hydrogen. Although we burn different things, in every case, the substance that we burn, the fuel, combines with oxygen in a chemical reaction that releases energy, usually heat and light, and often sound. Reactions of this type are called combustion reactions. Energy isn't the only product of combustion reactions, but usually the other products are treated as waste. For example, when we burn coal, it produces carbon dioxide as well as energy. And when we burn hydrogen, we get water as well as energy. In both of these cases, the chemical products are gases that we leave to drift off into the atmosphere. Some combustion reactions are very fast. If you mix hydrogen and oxygen gases before setting them alight, the reaction occurs in a split second. We call it an explosion rather than burning. And it's the same inside a car engine. The fuel is mixed with air in the cylinder and explodes with a spark from the spark plug. But put the same fuel in, say, a camping stove, and it burns. It's the same combustion reaction, just happening at a different rate. Combustion reactions are incredibly important for the way we live. We use them to keep warm, to heat water, to cook, to move cars, ships and planes, for manufacturing and to produce electricity. But they're not always helpful, and they can get out of control.
So, and that's funny because that's actually the experiment that I did with the fire foam. That's why the foam didn't burn, because there was actually oxygen inside the bubbles with hydrogen, and so it just made a quick pop sound. So, boom, there you go. Just explain that experiment. So, can't go do the. She got an attitude. So combustion is basically what happens inside of your cells. So as you can see, it's a very exothermic and violent reaction, and that actually does occur in like all of the cells in your body. So that's why mitochondria are the real MVPs, because they keep you from basically bursting into flames. And so most of your cellular respiration, like where your metabolism like really occurs, and all of the cycles that break down sugars and create phosphates and things like that your body can use to energize different cellular processes. All that stuff occurs in your mitochondria. And that's where the whole like multicellular kind of situation first, kind of that theory first came from, is like single cell. So this cell was a mitochondria, and then it was like this other cell that was like tired of just eating everything, like was just constantly hungry, and it couldn't figure it, like I can't store energy. And so it's like, look, I'm always making energy and I don't never have nothing to do with it, because I just kind of sit here and it just comes to me. So maybe if you let me help you, you can help me. So boom, there you go, symbiotic relationship. The mitochondria was, the real MVP from jump, and, hooked us up for, for millennia to come. And we've been definitely doing our thing with all the excess energy. So thanks, mitochondria. I know, right? But it's crazy, like how something like so, and it's like microscopic, like it's a subcellular. It's not an organelle. Like, yeah, we'll get into that. We're gonna get to biology soon, but it's a subcellular structure, and for it to be so small but be so extremely important, it's crazy. So it's like, don't ever, count yourself out, because you just never know what you bring to the table. Like, you gotta know what you bring to the table, and then no one can make you feel small. Ta-da! Mitochondria brought a lesson with it. And so there are, yeah, I talked about, and so now, so I know a lot of like compounds and stuff. Like I said, pretty much everything that's organic has carbon in it. And so like one of the things that have carbon in it that is bad for us is carbon monoxide. It is an odorless, tasteless gas. And the problem with it is that it binds very strongly to your hemoglobin, which is the protein in your blood cell that helps bind, that binds the oxygen to your blood cells and allow it to aerate your muscles and things like that, and bind carbon dioxide to carry it out and let you breathe it out as a gaseous waste. So when carbon monoxide enters your bloodstream through your lungs, it binds to your hemoglobin, and then it locks up those binding sites. So now oxygen and carbon dioxide cannot bind to them. So you end up in what they call anemia, hypoxia. Basically, you have low blood oxygen, and it creates an anemic situation, like an acute anemic situation. Like, trust me, if you have carbon monoxide poisoning, you will absolutely know it. So yeah, you can bring up the infographic for the carbon monoxide symptoms and
Okay, was that my cue for the video? I could.
no, not the video. It's the pic, the carbon monoxide pic. Mm-hmm. Yes. So that is why it is the silent killer, because you do not know that you have carbon monoxide poisoning until you have carbon monoxide poisoning. Like, you don't know if you're in danger of carbon monoxide poisoning because you don't know when these things are leaking this stuff. So things that use gases, so like a gas stove, a gas furnace, fireplaces that aren't properly cleaned and aerated, water heaters, because they tend to use gas to heat the water, running engines, so cars. That's why people can commit suicide using a car. They block up the pipes and it lets the exhaust run back into the car instead of out of the car, and that's how they die, from carbon monoxide poisoning. And the symptoms, the signs of carbon monoxide poisoning: nausea, vomiting, dizziness, what is this? Shortness of breath. That's what I'm saying. Like, your lungs can't even bind oxygen because the carbon monoxide binds to your bronchioles, like, because your lungs are full of blood vessels, and that's how the blood carries the oxygen from your lungs. So you'll feel like your body will tell you need to breathe more. We're not getting enough oxygen. So you have like quick breath, and it's like, I'm still not getting enough air. If you're asthmatic, you will understand this. So that might not be a symptom that you will recognize. You'll probably think you're just having an asthma attack. So you would have to pair the other symptoms with it to understand that you have carbon monoxide poisoning. Vomiting, headaches. So your brain the headache is telling you, like, I'm not getting enough oxygen. So that's what the headache is from. And then the vomiting is just a physical response to, alert you. And usually, like, anytime your body experiences toxicity, it usually triggers your stomach to make you vomit, because it doesn't know what the toxin is. So it's just trying anything until you feel better. And men, and this was a crazy fact I did not know, men are 2 times more likely to be affected by carbon monoxide poisoning than women. Not sure why that's a thing, but I'll definitely look into that. And if I find any answers, I'll share them with y'all. So, oh yeah, I didn't really say much about germanium, because it's kind of like fluorovium is rare and unimportant. But it's just used like how all the other semiconductors are. It's a semiconductor. It tends to be used with matter of fact, I talked about it last week with not boron, the one under boron. It'll come to me. But it's no, it is. It's treated with boron, and it actually makes a semiconductor that way. They call it dosing. So the germanium is dosed with some boron. So you're gonna see a lot of interaction between the group 3, group 4, 5, and 6 elements. So that's the boron group, carbon group, nitrogen, oxygen, and then the halides. The halides are bomb. I can't wait till we get there. Okay. But we talked about tin, lead. So lead is also why lead poisoning is bad, because it acts like carbon, but it is a metal in our body. So like metal in our body is not good, but it acts like carbon. So it binds to stuff it's not supposed to bind to, and it causes liver toxicity. So lead poisoning is bad for you because it quite literally poisons your blood, because your liver can't detox it from your body that well. And especially if your liver is already under stress and strife from, if you drink a lot of alcohol, not enough water, you don't eat enough, antioxidants, green leafy vegetables, fresh fruits, things like that. All those things help keep your liver nice and healthy, and avoiding toxins like alcohol. Alcohol is a toxin. That's why if you drink too much of it, you can absolutely die. That's what alcohol poisoning is your blood alcohol level gets too high, and you literally poison yourself. So that's why just don't. And what was I with so now we're getting to the good stuff now. Okay, so this group is cool, and they call it the P block group. So basically, that's where like I said, the p orbitals first start. So all the elements in especially like the first kind of row or period, all the way across. So boron, magnesium, calcium, and the higher up hydrogen, helium, those don't have p orbitals because they don't have enough electrons to fill those p orbitals. Carbon is the first in the smaller elements that has a p orbital. So they call it the p block, because that's also where all of their valence electrons fall. They fall into a p orbital. So the next one would be the d block, because all of those, that's the first one that has a d orbital. I don't think nitrogen has a d orbital. The one below it does, but that's usually where the d orbitals would start. And then you have the f orbitals. So as you get more and more electrons, they need somewhere to be, because they all can't fit in the same orbital, the same space. And then, like I said, as the nucleus of these elements get bigger and bigger, it has a much larger positive charge, but there's also a ton more electrons. So there's going to be an even number of electrons to balance it out. Not even as in like 2, 4, 6, but if there's 7 protons, there's going to be 7 electrons. So that's how they balance it out. And so as you get more and more, you're going to run out of space from, where the positive charge is pulling them in. So that's why the ionization energy tends to decrease. There are some groups that don't follow that trend as well or the same, because there are some elements in there, and the transition metals are kind of weird like that. That's why we skip those, and we'll come back because they get kind of complicated and they do their own thing. And yeah, it gets jiggy in the middle. So that's why this group is nice and uniform, because it follows it. So as you get a bigger and bigger element, you get a lower and lower ionization energy, because those electrons are further and further away from the positive charge. So they're more readily released. And that's basically what that whole thing is about with the p orbitals. And now this is a little bit of quantum mechanics, a little bit of that. So the Heisenberg and uncertainty principle is probably not pronounced that because he's German, so it's probably I don't know German, so I don't know how to. I'm not even gonna attempt that one. But he was a German scientist who actually had challenged some of the earlier findings and things in quantum physics, and what he came up with was groundbreaking and revolutionary, and it completely changed how science looked at science. So it was a pretty cool situation, and I got a video for this. I got a video. And he actually digs into Schrodinger's cat. Schrodinger was kind of one of those dissenters when he popped up saying that you can't know all of this stuff about a particle at the same time because of the nature of a particle. So I'm not sure if people are aware of this experiment, but it's like a super famous experiment, especially if you've taken any upper level science classes. They've definitely mentioned it. It's the single slit experiment, where they shot a beam of light through a slit, but instead of it just having the particles show up in one line like you would think, it actually split into several different lines, and it had like these little spaces in between them. And okay. And so that was like strange. So what they did was they set up a camera at the slit to see the particles go through the slit. When they did that, they ended up with a single line. And it was like, hold on. This is the same photon source. Why is it doing that? So they turned the camera off, and it was like, okay, well, we're going to try it again. So they did it again without the camera watching it, and it broke into these different slits. And it was like, what is going on? And then they turned the camera back on, like, we're going to watch it real close this time. And it turned back into a single slit. So Heisenberg explained that because light is actually moves in waves, and that's where they got the waves from. And then they also found out that particles also move as a wave. And so because it can act as a wave, but when it's viewed, when it's actually observed, it acts as a particle, say a single point particle. But as a wave, it's not one particle. A wave is like, so that is what happens with the Heisenberg uncertainty principle, is that you can't know a particle's position and its momentum at the same time. Momentum is a function of space over time. So if you have to pinpoint a position in time, you can't get its momentum because it's technically not moving. If it is moving, then wherever you saw it, it is no longer there. So the more precise those measurements get, the less you know about its other situation. So that's one of those mind-blowing like things. And then Schrodinger was like, well, what if we tied this to the fate of a cat? And then every time our detector detected a radioactive decay, it would open the poison and kill the cat. And it was like, what? So yeah, so that's where the curiosity killed the cat came from. That's actually what it's talking about. So basically, without the poison and detecting the radioactive decay, so a simpler version of Schrodinger's cat is basically there's a cat in a box. Is the cat alive or is it dead? You don't know that because you can't see the cat. But because you don't know if it's dead or alive, it is both dead and alive at the same time. So that's the superposition of these two phenomena occurring at the same time. And it is actually in reality true that the cat is both dead and alive because you don't know. Once you open the box, if you look in the box and the cat is dead, you killed the cat because you was curious and wanted to see it. So that's where that expression curiosity killed the cat came from. I know, right? Who knew physicists would be philosophers at the same time? You got the video ready for the Principl? I know, right?
He knows a lot about the science stuff.
Okay, there we go.
Dave explains.
Yeah, it was just lagging.
Once Schrödinger and pals had sufficiently developed the brand new field of quantum mechanics, some perplexing implications arose. For one, in classical mechanics, an object will have a precise value for its position and momentum at all times. In quantum mechanics, this was no longer the case. If a quantum particle were to have precise values for position and momentum, it would simply be a particle. But all particles are also waves, so this kind of determinism no longer applies. Instead, as we saw with the Schrödinger equation, the quantum realm is probabilistic in nature. This brought about the issue of how to describe the position and momentum of the electron. Under the Copenhagen interpretation of quantum mechanics, an electron simply does not possess precise values for both of these parameters at the same time. So, when we take a measurement, the result is randomly drawn from a probability distribution. An electron will seem to be in a particular location if and only if we measure its location. However, if we know its location, we can no longer know its precise momentum, or what it's doing. And this notion is summarized in Heisenberg's uncertainty principle. This states that when looking at complementary variables, like position and momentum, the more precisely one parameter is known, the less we know about the other. Here, delta x represents the uncertainty in position, while delta p is the uncertainty in momentum, and their product must be greater than h over 4 pi. If the uncertainty in one parameter decreases, the uncertainty in the other must increase, and if one becomes known with total certainty, the other becomes unknowable. The important thing to realize is that this has nothing to do with our measuring instruments. This is a fundamental quality of matter. We can't reduce an electron to particle-like determinacy, as it is also a wave, as was demonstrated by the double-slit experiment. Furthermore, this forces us to examine what it is to make an observation. To know the location of an object, to see it, at least one photon must hit our eyeballs. But if a quantum system interacts with even just one photon such that it can be seen, that interaction itself will alter the state of the system. So the seemingly innocent act of observation has a concrete impact on the system. When this problem of measurement emerged, the scientific community was in total confusion. This notion and the idea that nature was not deterministic, but rather probabilistic on the most fundamental level, had incredible philosophical implications, and many scientists developed thought experiments to elucidate the absurdity of a probabilistic universe. The most famous of these thought experiments was developed by Schrödinger himself, as he could not accept the Copenhagen interpretation. It is called Schrödinger's cat, and it focuses on the bizarre concept of quantum superposition. The idea is that if the Copenhagen interpretation is correct, a quantum system can exist in a number of different states, and until the system is observed, it exists in a superposition of all these states. Once observed, it collapses into one of the definite states according to its probability. Schrödinger did not like this, and he came up with a paradox. He supposed that there was a box containing a single radioactive atom. At any given moment, this atom has the potential to decay, emitting a high-energy particle. Inside the box, there is also a cat, a flask of poison, and a device with the ability to detect radiation. If the device detects that the atom has decayed, it will trigger a mechanism that breaks the flask of poison, and the cat will die. If it does not detect this, it won't, and the cat will be alive. The problem arises when we isolate this system from observation. According to the Copenhagen interpretation, the atom is in a superposition of decaying and not decaying, which seems pretty abstract and harmless. But because of the mechanism in the box, that means that the cat must be in a superposition of dead and alive. Only once you open the box and look inside will you observe the cat as being one or the other. Schrödinger meant for this paradox to discredit the Copenhagen interpretation, but there are many camps that believe that this dead-alive superposition is a concrete reality. This thought experiment remains a classic, and it is frequently referred to when comparing different interpretations of quantum mechanics. But enough about cats. Let's finish up with Heisenberg. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Buddha. Oh, don't bump your head. She doing her little fallout because she got an attitude. It's also a personal problem. Buddha. So the set Buddha. She wanted to type. I wouldn't let her type because she will shut all of this down. So the second part that he was talking about is this same principle applies to energy and time. And as my co-host and you the co-host and production team said, that is also the concept that they used in the Ant-Man movie. So basically, the more you try and measure the amount of energy in the system, the less you know about time. So you can't measure the total amount of energy in the system with reference to time. So time is a finite thing. It's a limiting factor. So you will either never know all the energy in the system, or you have to operate outside of time to do that. And yeah. So I was like, oh, mind blown. Okay, boom. So you see how that becomes an extreme. That's what I had to think of, man. So that becomes an extremely deep philosophical thinking exercise, because you can apply that to like pretty much anything, especially when you feel like I don't know, like confused about something. It's like when you think, the harder you think about it, the fewer answers you get from it type situation. I've been in that one a whole lot. Heavy on the mind. Yeah, that's the type of message. Yeah. Knowledge that'll melt your brain. Yes, for certain, Marley King. Yes. And so, but it definitely does help expand your mind. So the more you think about difficult concepts and things like that, it makes new connections in your brain, and it actually helps keep your brain healthy. So the more you do that, the less you have to worry about things like Alzheimer's and dementia. Those things tend to come from if you don't use it, you'll lose it. So not just the degeneration of your brain cells, but also just the use of your brain. So that's why they tend to treat those type of conditions with interact. I don't know what they call it, but it's a certain type of therapy where they basically just give them projects to do. Like, you know, like my daughter, she actually got a bunch of knitted blankets from the nursing home that donated it to the center that I was getting my pediatric care from, my what do they call it? Prenatal care. So that's how they keep their, their brains in use. They paint, go, nature walks, stuff like that. So staying active is definitely key to staying healthy. And that being said, we're finna get all up in the carbon in your body. So you can bring the picture up with the different categories for yeah. Yes. So I like totally nerded out on this. So I actually have like a little cheat sheet. I'll show y'all when we get done with this. But so a monomer is basically one single subunit of a larger structure. It's like the smallest possible I would say molecule of or compound of these things. So carbohydrate is, as we know, carbs. So that's what we're like, oh no, carbs are bad. They are not bad. That's where you get the bulk of your energy from. And that's also like your immediate energy. So they're very useful, especially if you don't overdo it and you're very active. And this is also the first form of energy for your brain. So if you've been studying, you study hard and you get like headaches and stuff, or like you get like a craving for snacks, like sugary snacks, that's why, because your brain needs energy right now. And it's, trust me, it's going to use it. So you can actually end up burning the same number of calories just thinking really, really hard as you would if you like went for like a 5 or 10 minute jog. Crazy, huh? Yes. The brain is powerful. Feed it. So you have what's called a monosaccharide, and saccharide is just the technical term for sugar. So that's all it is. And a starch is what is called a polysaccharide. But it's a polymer because it's a bunch of monosaccharides linked together. So it becomes a polysaccharide. Usually they just add poly in front of stuff to say it's more. So you get one or a bunch. That's that's all you get. And then like they have like dimers, trimers. A dimer is just 2, a trimer is 3, and that's where triglyceride comes from. I'm telling you, I tell people my brain works like a for real computer or phone. There's no off, yo. Yes, actually, your brain is more powerful than the biggest, largest, most fastest supercomputer in the world. Your brain is like whatever. It's like the sun, and the supercomputer is a star, like a little teeny tiny boop, a little boop, a flashlight boop compared to your brain. Yes, that's exactly. So they're still uncovering like stuff about the brain, a ton of stuff that they don't know about the body in general and the world in general, and all of that. So like I said, STEM is fun because you get to explore stuff in the world and learn stuff and teach each other. So that's why we're here. And then the cellular structure for because starches are only found in plants. You're not going to find starches in nothing animal based or whatever that has like a heartbeat that doesn't do photosynthesis. So starch is a sugar product of photosynthesis, and they are stored in granules in chloroplasts. So that is the multi structure, or the cellular structure, where the polymer starch is found in plants. Then you have nucleic acid. This is the base pairs of a double helix. So your DNA is made from nucleotides that are linked together in a certain order, and you get 2 strains of those, and boom, you got the double helix. A single helix is, a single helix. And then RNA actually ends up attaching. So RNA has different base pairs than DNA, but they're complementary. So it just changes the base on the nucleotide for RNA. So I think thymine, I want to say it's thymine that's replaced by uracil or something like that. But there's one base pair that's different in RNA and DNA. And that's why it can move in and out of the nucleus, kind of like, so the nucleus know, like, wait a minute, are you taking it? Oh, okay, you're not DNA. You don't have the right base pairs. Go ahead. Like, it's like a check to keep your DNA where it belongs. And so the nucleotide, as you can see, has a sugar and phosphate group that attaches to the base pair. And that is basically how your body breaks it down. So it breaks down the sugar, it metabolizes the sugar in a combustion reaction, or a hydrolysis reaction. So water will come in and break the bond between the sugar and the base. And then now you have a free base pair. So the base on there that you see there, that's actually what your DNA uses in that double helix. And then your double helix expands and all of that stuff, and boom, your cellular structure is the chromosome. And the chromosome is just a very dense collection of DNA. And then the protein is the amino acid. So the amino acid is the actual structure of the base pair that you see on the nucleotide. So the amino acid is called an amino acid because it has an amine group that has nitrogen in it. So that's what they call amine, nitrogen. I don't know why. Like I said, the names can get weird, but when you submerge yourself in that terminology, it just, you don't even bother asking, like, okay, you just know nitrogen is in there. And then the R group is actually a any other type of functional group. So whatever functional group you will put in there, that's what R is. And then it's always going to have a carbonyl group, which is the carbon, the CO double bond with the COH. So that's where the hydrolysis comes in. So that's where your base pair would have been attached, where that oxygen is, but instead water came in, cut the base pair off, and then left hydroxide behind, and that's how you get that. So a polypeptide is just a bunch of those linked together. So that's where the OH group comes off, and then they connect, and then you end up with a long chain of those. And then those come together and form intermediate filaments. So your muscle fibers, your body tissue, your skin, all of that stuff is made of proteins. Your hair, your nails, proteins, and all of those become some type of filament. And depending on how those amino acids are linked together is going to determine the hardness, the friability. So like how your nails are like hard, but your hair isn't. That's the difference in the protein. Like you have, I think, like keratin in your hair and then something else in your nails. You got some keratin in your nails too, but I think it also has like chitin or something in it that makes it hard. And then your lipid, so fatty acid. So you probably heard of these. Those are the omega-3s. Those are fatty acids. That's what they look like. Triglycerides are just 3 of those fatty acid chains linked together. And those because carbon dioxide is on there at the end, but there's a hydrogen group, so it's a carboxylic acid group. That's what that is. So once the hydrogen is taken off of there, it becomes extremely polar. And so the CO2 end, where you can see on the triglyceride, so that long blue and black chain is hydrophobic. And so you have a cellular membranes are made of triglycerides, and that's because they are polar. So there's one end that is hydrophobic, which is the long fatty chain, and then there's one end that is hydrophilic, meaning it loves water. So that's your carbon oxygen end because it's polar. And so what happens is you get proteins that sit in that little those are called heads. So at the the carboxylic acid head, you'll have little proteins that sit in there and either get activated to open up and allow things through, or if things are polar enough, it can just pass through the membrane itself. So it'll pass through the top on its own and then just be pushed through because it's it's water based. So it just literally gets pushed through the hydrophobic part because it doesn't like being in there. So it's going to enter the cell quite quickly if it's polar. And then if it's non-polar, then it has to enter through those protein channels and usually have some type of energy that needs to be exerted to do that. And they're what's they call like passive. You have active and passive metabolism, and that's what that has to do with, or transport, active and passive transport. And then the cellular structure of those is adipose cells. So those are fat cells. So the little circle on the side, it's like a little small dark circle. That's actually the cell nucleus. And most of these cells have no other organelles. There's no mitochondria, no Golgi bodies. Like if you even taken basic biology, you've seen a cell and it has all these extra stuff in it. Adipose cells do not have any of that stuff. It has a cell membrane and a nucleus. All the rest of it is just storage space. And so what happens is when your body ends up running out of space to store this fat, it ends up creating new fat cells. And so even if you end up burning the fat out of the cell, you still have the cells because your body isn't going to just get rid of them, because it's like, oh no, because you're going to have to store it. You're going to need fat, you're gonna need somewhere to store the fat because your body is operating off of its equilibrium. Its equilibrium was we were storing this much fat. So that's why it takes a little bit longer to burn fat than it does to, well, not burn fat, but to get rid of like fat and the size that went with it, because you have to actually wait until your body is like, okay, well, she stopped eating all the stuff that we needed to, the extra room to store the fat, so we can start breaking these fat cells down. And then that's when your size tends to shrink a little bit more, and it's easier to keep the weight off because now your body isn't already prepared to store more fat again. So it's okay. It's a process and it'll take a minute, but you stick with it, stay consistent. Your body gonna break down those fat cells and get rid of them and all of that. And that's really what liposuction does. It just pulls out the fat cells, not just fat. Like fat has to be in a cell, so it pulls out the cells with it. And that's why if you actually change your diet, then you can not reproduce those cells, because your body is going to make new places to store the fat, because it doesn't waste energy. It's not ever going to waste energy. That's why they have like pills and stuff that you can take that makes your body like release fat or something, or not store it, and so you end up with like nasty diarrhea because it's fat. Like it's literal actual greasy fat in your excrement. So that is it for today. I went way on. It seemed like time like really flew by today. Like, what's going on? Like, is it just me? Like, you know what we did? We were trying to measure like all of the energy, and so we couldn't pinpoint the time because of Heisenberg's uncertainty principle. But the good thing, like the cool thing about it is like a lot of this stuff is talked about in several different ways throughout science. So like when I was in high school, the carbon cycle, we talked about that in environmental science. We also talked about that in biology. We also talked about that in physics. So you're going to get a ton of exposure to this like going through school. So that's not a worry. And then unless you go into a scientific based field, probably will never have to know any of this stuff in minute detail ever again. I had to actually memorize not just these type of cycles, because I didn't go into environmental science, but in chemistry, there's this thing called the Krebs cycle, which is basically something that occurs in plants. So we actually had to learn how plants make starch. The starch that I was telling you about that they store, we had to learn how they made it. We had to memorize the cycle. We had to memorize each individual like chemical compound that's involved, how many phosphates are used, like on not phosphates, but how many molecules of ATP, which is the cellular energy, so adenine triphosphate, how many of those were used, how much ADP is produced, where the other sort, like, yeah, oh, trust me, it gets it gets real saucy, okay? And I thought it was strange that like it was so much memorization to it, because I'm one of those like general concept people. Like once I get the concept, I'm cool with it. I don't need all the details, but they test you on the details. So I had to make a lot of note cards and things like that. So do what you got to do, okay? Because once you get out into the real world, they are not finna ask you any of that stuff. The most useful that stuff is in research. So if you're going into research, you do need to know that stuff to that minute of a detail, because the answer might be, in the details. So you have to know things down to that level. But if you're just doing like industrial like type processes and stuff like that, it's been brought up to such a large scale that the smaller details are less important than like ensuring safety, efficiency of the process, economic feasibility and stuff like that. So you don't have to actually know that. And then they tend to have other analytical groups that do R&D. So you don't have to do the research, the knowing, and the, cranking the whatever to make the system go. So the concept of these fields of science, technology, engineering, and math and things like that, the concept of those fields is much broader when you're learning it than when you're actually using it in practice or in a career out in the real world. But the information that is disseminated in any of those is invaluable. And if you pay attention enough, you can definitely apply it to real life. So when people are like, oh, I'll never use this again. I ain't never used an isosceles triangle information ever in my life. You probably just didn't notice it because you didn't deem it important. So when you gloss over the details, if someone is telling you to pay attention to the details, pay attention, because you just never know when you'll need it. Like, that's why I love MacGyver. Oh, that was my show. Okay, and I watched the old MacGyver. I watched the new one too. I like that one. They had, like, he was cute. I was like, okay, so y'all ain't get an ugly MacGyver, because I'd have been upset. But but like, MacGyver was my dude, because he was like, you put him in like the most messed up situation. He don't have nothing. He don't have no gun. He don't have no phone. He don't have no walkie-talkie, no earbud, no none of that. He was just out there, and he could come up with some stuff. And that's what really got me like interested in looking at like chemistry and science and things like that, because he used all of that stuff. He used all the STEM stuff: science, technology, engineering, math. Like, he had to like really, and like on the fly with, just regular stuff that he had on, like a bubble gum, paper clip, like a battery, and some wire. Like, what is he gonna do with that? He make like a helicopter or something. I'm like, how did he do that? And so that was like, probably, like, that was the coolest thing I had ever seen done with like the nerdiest subjects you could ever think of. And it just made me like, oh, I gotta get in on this club. And so that's what I did. And just the more I learned, the more I saw the connections and how everything was like really connected. And the more I started to understand about like the things I couldn't, because I'm terrible at math. Like, it was a struggle. I think I took math my entire time I was in college, but I only needed 3 years of calculus, but I had to take all of them twice. So, and I was in school for like 8 years. So yeah, that says a lot. So it was a struggle. And then even with a lot of like the quantum theory and stuff like that, it's like super high level math and like definite like instant migraines and stuff like that. So I was snacking all the time because my head always hurt. And but that's definitely it was definitely worth the headache. It was worth the pain. And just being able, math had me in summer school. It's okay. It's okay. We made it though. We made it to the other side. Okay. Now all I need to count is my money. Okay. So I got decent math for that. But just understanding like the difficulty of things and how we oversimplify things sometimes. And I was really just thinking about that earlier today. Like I'm trying to get into a new groove and like get up and journal and stuff like that, like just kind of free flow journal. And I actually, like, this is so crazy. Like, I actually ended up falling into this frame of thought, the Heisenberg uncertainty principle. Like, cause that, like I said, this was like a super like mind blowing thing. And then the prompt was interpret. And somehow I went from interpret to like space time and how time is like ill-defined, because it's like we think of it as linear when actually it's like multi-dimensional, and it doesn't confine things in the same way once you move out of the 3D. And even in the 3D, there are certain dimensions that's not explored or thought about because it overcomplicates it, because there's certain things you can't quantify. Like, I feel like emotion is a concept of time, because you can time travel with emotion. So if you think about a memory, the emotion is going to bring you back to that place in time. So you've literally just time traveled. If you think about a goal that you have or something that you want for the future, the emotion that's attached to that desire, that goal, that push forward, is going to pull you forward in time. So that's why like this whole kind of influx of like meditating and quieting your mind and like just being has gotten so important, because we're like literally pulling ourselves forward, back, forward, back, forward, back, forward, back. We don't have we don't stop and take the time to sit with ourselves in the now, because what you do now, how you feel now, is going to determine your future. So if you're worried about the future, it's only a worry because you're not doing the work that you need to do now to make the future, something that you don't need to worry about, or something, make it turn out the way that you're hoping it actually does. Like, it always says faith without works is dead. So I'm not dying. Last time I checked, I'm healthy, and I ain't been walking, not looking both ways when crossing the street, so I'm not gonna get hit by a bus or nothing. Because I live on the 7th floor, so I don't even have to worry about people not driving properly, crashing into my living room and stuff, and not taking me out while I'm watching TV or something like that. So that's something that really kind of was like, dang. And then it's like, of course, I look at the carbon wheel. I'm like, well, what am I finna talk about? And then somehow I looked up the p orbitals, boom, Heisenberg uncertainty principle. I was like, I literally just thought about this earlier this morning before I sat down to really get into the information I was going to share with y'all. So I was just like, this is a message. All right. So it's just and then also the space, time being linear, and then the actual space it takes up, was the emotion part. But I was like, the expansion of that is frequency. So it's like, people are talking about vibes and vibrations and things like that, but emotion is tied to that as well. So when you feel sad, don't you feel like, less energetic? Your frequency tends to be lower. You tend to want to listen to slower music, even might be something they might talk about on RockTrue Beats, which is coming up next. I think in 30 minutes. I went way over today. I don't usually do this, but yeah. It was a lot to cover because carbon is super important. But yeah, so I was just thinking frequency. So your vibration, and if all the particles, so every particle, every single atom is a wave, that means your whole body is a wave. And what are waves? They are frequency. Doom. You see how that boom. Okay. So, we learn this stuff. All right. So you can adjust and with the Heisenberg uncertainty principle, if you're living or emoting in the past, you don't know what your current position is. You can't, because your emotion has pulled you out of the present. So you don't know what your momentum is. So your progress or none of that stuff, because you're focused on the past. If you're too focused on the future, you lose sight of the past, the steps, the actions that you need to take now to ensure that the future that you're desiring and hoping and praying for actually comes about. So it was a mind-widening realization for me. I don't know if anyone has talked about that or crystallized it from a thought to words to disseminate to people, but that was definitely a fun prompt for me. And I actually folded that page in my journal so I can make sure I find that again. So I'm like, I'm gonna need this again soon, now, and later. So that's my little share for the day. I'm gonna get ready to tune in to RockTrue Beats because I know they're gonna come with the fire like they always do, getting y'all out of the death culture, the culture of hate, and into love and good vibes and life and light. And I was just thinking about even just old songs. I'm like, dang, even the old songs, they probably wasn't. And then it was when you hear them now, it's oh, they really wasn't talking about love, but they wasn't real just nasty and let me get it, girl, ha. Let me tell you, and I'm like, I thought this was a love song. Why they singing like that? But it's the nice old even just the do they got the nice little vibe. So that's just how I kind of vibe with the music that I listen to. And then I even end up thinking about stuff like science. It's crazy. So whatever is bumping around in your mind, I definitely suggest writing it down, because sometimes you might mess around and get a message and you got to share it. And if you didn't write it down, then you got the message and it just went do 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 do, and somebody else then picked it up and they wrote it down, and now they gonna take it. Hey, I just thought about that the other day. Well, you didn't write it down and you didn't share it, so boom, on to the next one. Hey, Native Princess Danye. So that is our show for today. We are going to talk about nitrogen group next week, and they have their own little situation going. So the boron group made 3 bonds, and carbon group makes 4 bonds. The nitrogen group is odd in the fact that it makes 5 bonds. It can make 5 bonds. Nitrogen itself doesn't. Nitrogen actually will end up only making 3 bonds, which is strange for that group. But all the rest of the elements will make 5 bonds because they have more valence electrons. So yeah, that's one of those groups where not everything in it is going to follow the trend, a nice little neat trend. Like if you go down the group, everything is going to increase or decrease in the same direction under that same thing. Sounds like a soap opera. Yes, it does. It get messy. It start getting a little messy. But that's why I like the halides, because they real strict with how they do. I don't care what size it is. They probably really only going to give up 1 electron because they just like, I'm almost a noble gas, so this all I got for you. Like they real kind of stingy with they stuff. Yeah, okay, yeah, we'll take that one. So yeah, they taking stuff. So you know, curiosity killed my cat. You done? Yes, that is actually yes. So remember, think on things that expand your mind. Be curious about things, research things, ask the question, because you are not going to get answers. God even tells you, if you ask, you shall receive. And that includes if you ask for answers, you will receive them. So make sure that you are asking the right question, because you might be expecting a different answer, but you didn't ask the right question. So, research. That's why we went through the experimental method. You get a question and then you research it so that you can make sure you are formulating a nice and clear question to get a nice and clear answer. So this is definitely a nice exploratory subject, especially like, you know, those philosophical tied to science, and you'd be surprised at how much competition has pushed forward advances. So if you have to, hey, bring a friend, okay? Phone a friend. Hey, what you know about what you think about? And then if they have a opposing or a different perspective, don't be like, oh well, no, you wrong. Like, consider it, because hey, it's probably true somewhere, or they wouldn't have thought of it, huh? Maybe, you know. So I love doing that, considering different perspectives, and even, you know, helping people make it where it's viable. Because just because I don't necessarily agree with it doesn't mean it can't be a viable, you know, opposing or different solution or perspective. It just has to make sense, you know. You can't get water from a rock, right? At least not with our current means. See, that's keeping that open mind. So that is enough for today. I will see you all next week with our nitrogen group, and tune in 30 minutes for Rock True Beats and Rock Truth, or nothing at all.